Before we start, I'd like to say that Shehin, the previous speaker, has been writing for our journal of proof of concept, or the other thing. The copies of that were distributed last year at H2HC. You can find them online. And Shehin writes a series of articles on system boot. And if you want to understand the earliest stages of system boot, these are the articles for you to read. So look for the previous 2 copies of PSU GTFO online and read Shehin's articles. They are very concise and yet very informative in how things work at the earliest stages of the boot. Yeah, partying has been great, except my voice is gone. So the thing about the sort of parties that we have here is that it's quite impossible to keep the voice by the second day. Okay. Let's start. This talk is about old bugs. Well, bugs from the last 2 years. And those bugs have been really, really simple. And in each case, the actual missing thing that turned a bug into a famous bug was a simple oversight. So hence the title of this talk. Thank you. Yeah, hence the title of this talk. You know, it's a children's poem. For want of a nail, a shoe was lost. For want of a shoe, the horse was lost. And for want of a horse, the rider was lost. And for loss of the rider, the battle was lost. Then the kingdom, and it sort of goes from there. So a small thing that propagates cascadingly and creates this enormous failure in the end. You can sort of write it down in a formal way. You know, no nail, no horseshoe, no horse. But very often, when a simple mistake is made, something is gained, right? And that thing is usually a pony when we're talking about bugs. So that's how bugs get famous. And we're going to talk about those famous bugs in 2013 and 2014. And the thing about them is that they were all simple and avoidable. So, you know, just exactly that case when you should have shoed your horse right. And of course, what we want to do is eliminate those classes of bugs. And so every time we see that sort of thing, we ask ourselves, we should be asking ourselves, what went wrong and why it went wrong? And when a certain kind of a mistake gets made all the time, and by people dedicated to what they're doing, well, maybe there is some bigger principle at work. Maybe there is, this is time to step back and see if we are actually thinking about the topic right. Maybe we don't have the right model for parsing, for input processing, for validation, and that's exactly what we're going to do. And so you could say hindsight is 2020. Of course, once the bug has been discovered, it looks simple. To which I would counter. There's another thing that we know as hindsight, and this is work safety rules. Simple rules like don't check for voltage with your bare hand, right? There's a saying in Russian that workplace safety rules are written in blood, because behind each and every simple rule, there is a gruesome accident. Well, such simple rules, I argue, are long overdue in software, because in software, it's usually actually not even the developer who suffers, it's the end customer whom this industry calls the user. And as Felix Lindner, FX, says, there are only two industries that call their customers users. That's the drug industry and the software industry. Interestingly, neither has liability. And so there are all sorts of simple rules, like don't stack your bricks too high. These are, by the way, Russian posters, and they were very graphic. And possibly this was because people who were supposed to read them and profit from them did not all know how to read. So that is an interesting culture, right? So, don't stack your bricks too high. Don't stand under towers where people work. Don't dig yourself under loads that can fall on you, and things like that. So we have a similar situation in software engineering. There is a persistent anti-pattern that keeps getting us. And we talked about those anti-patterns in 2012 at our Brooklyn talk. The video is online. We called this shotgun parsers because the anti-pattern is that the checks for input data, the checks for validity of input data are scattered ad hoc, just like a shotgun pattern of pellets goes all over the place. And you don't actually aim a shotgun, you just point it, as they say in that business. So scattering random validity checks through your parser is not going to protect you. You have to do better than that, especially because in the parser you can actually you actually need to malloc, memcopy, do arithmetic, and all the other juicy things that the attacker just loves you to do, because that leads to memory corruption, overwrites, and that sort of thing. And it is worse when the protocol syntax is complex and what we call context sensitive. So there are famous examples of people who cared. Well, bind 8.4 was our first example. OpenSSH 3.3 pre-authentication vulnerability, pretty damn bad, right? Pre-auth remote code execution, exploited by Goebbels in 2002. Then OpenBSD, again, people who care about security, people who took pains to write their code securely. Nevertheless, the 4.0 version in 2007 was vulnerable to an ICMPv6 fragmentation attack and was remotely exploited by core security. So, and those were pretty complex bugs, right? Also made the ponies at some point. So those were pretty complex bugs. Say, for example, in bind, the DNS next record overflow exploited by ADM took advantage of the fact that DNS uses hostname compression. So whenever you have a host name, right, in the first and several records in the DNS packet, the names do not repeat. Instead, they back reference. So if you've already seen that substring, you get a back reference in the packet. So when you assemble the name fully, you don't actually know how much space it will take until you traverse all of the records backward, all the back references, and then you assemble the name. And then, of course, you need to keep track of the length of all the strings you encounter. Yeah, this is where a mistake was made in C code, as you would expect. So very interesting bug, very instructive, and of course, a big deal because DNS is your core infrastructure. Then OpenSSH, pre-auth challenge response. The exploit was due to Goebbels. And the stream of SSH options in the challenge response was parsed And again, if you look at that parser, the parser was carefully written, except the part where variable option lengths, option length, option, option length, option, where all those option lengths had to agree across the entire stream. And if they didn't, then you threw away the packet, the stream. Except by that time, you've already allocated memory. And you've already corrupted memory, and this is how the exploit was done. So another case when a complex format with several integers that must sum up to the end of the packet, and you don't know if they actually summed up until you've scanned the packet entirely. Again, a subtle bug, a complex format. Very well. OpenBSD 4.0 and the ICMPv6 fragmentation attack. So IPv6 headers chain. If you listened to Fernando's talk yesterday, you have had a taste of that. And those are complicated data structures of variable length, back to back, a whole chain of them. Now, BSD keeps its packets in chained buffers. Again, another chain. And so you had the two chains of variable length structures with pointers, and you had to reshuffle that heap all the time, because when you process a header, it had to be contiguous in memory. So it had to be in one chunk. A very interesting bug, again, very gracefully exploited due to, again, a complex format and good luck keeping two pointer chains in sync perfectly in C. The common pattern was that, a complex format requires a whole lot of paranoia, right? So up to a certain point in your code, you're totally paranoid, you're checking everything, or you think you're checking everything, or you should be checking everything. This is called input validation, or we call it recognition. And as you remember, our recommended approach, language theoretic approach to parsing, is that you should actually define the grammar of your valid or expected inputs. So recognition should be really what you're doing there, whether an input fits that grammar. And then, of course, you have to do work. So there is this boundary after which you trust your previous checks, you trust that the data is as you recognized, you trust that the input is as expected, and then you can actually relax, hope that those checks will have your back, and you can do malloc, you can do memcopy, you can do arithmetic. In theory, this is how it's supposed to be, right? First you check assumptions, then you rely on them. In reality, this is how it turns out in most code, right? So first of all, forget recognition or validation. People tend to describe input checking as sanity checks, as if sanity was some sort of a property that you can check on input. And, well, yeah, good luck with that. There is also sanitization. Sanitization is an anti-pattern. Do not sanitize input. This presumes that you can somehow recognize badness and remove it, and the rest is okay. And again, this doesn't work. You are going to miss some assumption, and you're going to then rely on it unchecked, and you will fall, and nothing will have your back. And so the more you intersperse those things with the things that give power to your attacker, say memcpy or malloc, the power to actually shape your heap or corrupt it, the more you will suffer. So there has to be a clear border when you've done validating input and when you can do work and when you are still doing it. But that's not all, because another part of that common pattern is that your if your syntax is too complicated, you're almost guaranteed to fail pragmatically. So if you have redundant fields, which must have matching dependent values for the protocol for the protocol payload to be correct, then it's very likely that you will forget one of the checks, and you will rely on one field being agreeing, matching in value with the other field, and you will forget to check that, and those fields would be different, and you will suffer. A clear example of that is when you have nested fields with variable lengths. So you have a containing field, and then a field inside it, and they both have lengths, and you forget to check that this is the case, that the containing length agrees with the contained one, right? And then you would perform some memory allocation, and then you would perform some memory copy, and the disagreement between those fields will get you. So values that must agree across layers and objects in the packet, when you have to remember what you had seen on a layer 1 or 2 deep than the one you're now operating at in the layers of, across the layers of abstraction. Again, this is a recipe for disaster. And all those lead to this thing that, to this pattern that a condition is assumed and not checked. So if you look at the characterization of those formats, then they agree with languages. So the classification of languages starts with irregular languages, those that can be parsed with irregular expressions fully, a finite state automaton. Then it goes to context-free languages that can be parsed by push-down automata, stacks. And then it goes to context-sensitive. And already a single value, length value, and then the variable field of that size gives you weak context sensitivity. Length fields that must agree across many objects give you strong context sensitivity. It's much better for you, and it provides for much simpler parsers to keep your languages context-free or regular. So if you don't, then you are going to be exploited, and you're going to have a weird machine in your code. And essentially, context-sensitive syntax and ad hoc parsers are guaranteed to provide pwnage. So, you know, we talked about this in 2010. We talked about this in 2012. What's new? These years are really, they could be called years of the simple bugs, or even dumb bugs, except that I feel that this is unfair to blame the developers on those bugs, because as you will see, the context sensitivity of those protocols that they were made to implement is quite high, and it's really a non-trivial task. So whether the bug is bad, or whether the bug is dumb, or the format is too complicated is an open debate. So what's new? Heartbleed, right? A very simple parser bug. Go to fail, right? A very simple bug in the implementation of protocol state machine. Does it get much simpler? Android master key. A differential between between how data is validated and how it's seen when it's installed. And Nginx chunked HTTP encoding overflow that has been discovered in Apache 10 years ago, and it took 10 years for this new error to come to light. So these are the bugs that pretty much dominated the pony scene, and there are many more parser bugs. We'll just talk about those. and they all got the ponies, so they're famous bugs with the little stars to their name. So first, heartbleed. Let's look at the syntax of SSL records. So here is a heartbeat message. Again, standard SSL syntax. You have a containing record. That record has a length. That record, pointer. That record has a length. And then it contains a sub-record, the actual heartbeat message, the payload. And that payload has a length as well. So you have two lengths that must agree, right? So that should clue you in that this is where a check will be forgotten. And indeed it was. So despite the overall length being just 4 bytes, the heartbeat message claimed that the payload was this long. And so the payload that was supposed to be echoed, guess how many bytes of that were echoed? You know, as many as a 2-byte integer would fit. So that was the essence of the bug. Essentially, 2 fields that had to agree but were never checked. And the heartbeat message should have been discarded. Instead, it was processed. And if you look at the code that is the parser code, it should have been the parser code for those messages, you will see why, right? So here's a pointer that runs the length of the message and looks at the payload, which should have been short, and the check was not done. And then, this is how you memcopy the payload back into the response message. So you just go by this length. So you should have discarded this, but you didn't. Now, I ask you, is this a parser? Does this look like a parser to you? Can you guess what data format this code is expecting? What it is expecting to parse? And the answer is no. Well, let's look at the patch, right? So look at the top chunk. The top chunk was the parser, quote unquote, that was being removed. And again, looking at it, you have no idea what data it expects. And this is the fix, right? The second chunk. Read type and payload length. And you see 1 plus 2 plus 16, 1 plus 2 plus, what are those things, right? Can you guess what format this code is expecting? If you can't guess what this code is expecting, how can you audit this code? Is it so strange that this code was effectively unauditable? So here, the rest of the fix, at least some of those 1s and 2s are being given some explanation, right? So 1 is the heartbeat type, length, and the 2 is the 2 bytes with a heartbeat length. Okay, so we can sort of work with this. And then the variable, the write length, the amount of memory to copy back into the response also defines the semantics of this. But still, so many years from now, who can guarantee that another code just like this with fixed integers is not going to be vulnerable and can be effectively audited? So unless the code makes clear what it expects, good luck auditing it, right? So it's such a simple rule, right? I mean, how hard is it to work, to be careful to work with a shovel? It's that don't swing your shovel. You can hurt people. Simple workplace safety rule that was violated in this case. So your input is a language. Treat it as such. Write a grammar spec. once you have the grammar spec, make sure that the parser code reads like that grammar spec, and that you can see from the parser code what it is parsing and what it is expecting. Then you can see which conditions you've checked. If it's not clear from the code structure, then good luck. You are not going to audit that efficiently. So nested links are syntax. So this is important. When you want to start doing work, and when you want to be not on the paranoid side, when you want to be on the side where you actually do useful work, by that time, you should be done with checking nested links. Nested links are about data boundaries, and you should already have all the data extracted. It's too late to check whether nested links agree when you're already posed to do work. You should have checked them, and you should have discarded them in the recognition phase. So they must be checked in the parser. If they don't agree, the message is invalid. This is not semantics, this is syntax. This is not what the data means. This is even how the data is formatted. We describe this in the LangSec approach as full recognition before processing. Full syntactic recognition. Do not allow your semantics to happen before you know that the message is valid. And of course, as every internet meme needs a cat, you know, this is the LangSec cat. And if you can't paste images into your code, then here is a UTF-8 version of that you can paste into your code. Full recognition before processing. This beautiful, beautiful UTF-8 image was made by Melissa. And if you look at the whiskers on that cat, and the ears on that cat, and the eyes on that cat, there's nothing ASCII about this. This is Unicode in its full glory, right? So make the cat happy. Do away with your syntax recognition tasks and fully before you start allocating memory and doing other things. Okay, so go to fail. Wasn't that a nice one, right? So this is SSL protocol, and this was Apple's implementation, a hand-coded implementation of a state machine. So state machines are good. State machines are a clear model of how you consume input. However, hand-coded state machine is not so good because, well, states are usually circles, right? And transitions are arrows. Fine. And then when you look at this wall of code, wall of text, you can sort of see that structure, right? So if you make a check and you fail, or you proceed. You make a check, you fail, or you proceed. You make the check, you fail, or you proceed. And by the time you get to like the fourth state, your eyes glaze over, and then you cut and paste that go to fail twice. And then, of course, you skip all of the important validation. And this is bad. So this is a state machine done wrong. You should generate some code. A simple macro would have helped. Not to mention some sort of a code, a framework. So, you know, again, a very, very simple rule to observe, right? Don't step on fish as you're loading and unloading your fishing boat. It's easy to remember. It wasn't done. The results are deplorable. Don't step on fish. So this bug was not on the ponies, but misery loves company. So just not to beat up on Apple, GNU TLS about the same time had a similar parser bug, the so-called GNU TLS hello. You can see the part of the patch. If length is less than session length, then something. And then you see that it had to be fixed with another comparison, whether the session ID length was larger than it was supposed to be. Again, this is syntax. This is not semantics. This should be fully checked as you're checking whether the data is as you expect and it is valid. And a very good description of the actual memory corruption is on the Radar log, the technical analysis of the vulnerability. And just to see what it is about, again, we can look at the proof of concept crash that's here, that was written by Aaron Zoner. So here you can see the data structures for the proof of concept being assembled. So you have a type, and you have a version, and you have a length. And then again, this is the containing record. Then you have the protocol payload, again a type, a length, a version, and a certain random seed. And then again you have the length and the session data, which is a whole bunch of FFFFFFs, which I skipped. And look at this. This is 3 data structures. Let me advance the code so that you actually see the resulting data structure, right? You concatenate all of those and you get your packet. And these are nested data structures with the 3 links, and all of those links must agree. What does that tell you? A mistake will be made, and it was made, right? So now, before you can do anything with this message, you have to make sure that all of those length fields agree across all of these data structures. Good luck with that. GNU TLS didn't get that. That was the bug. So again, a very, very simple, a bit of advice that just wasn't followed. So here's another one. If you have 2 parsers and they have to parse a message, then very often the security of your system depends on the parsers agreeing. The parsers understanding message the same way. And we've seen this over and over again. In network intrusion detection, Ptacek and Newsham in 1998 showed that if your IDS assembles the stream of packets differently from your target, then the target will assemble the exploit, and the IDS will assemble something different just because TCP/IP stacks are full of parsers, and those parsers are all slightly different. So network evasion, NIDS evasion, has been known for quite some time. And it's a parser differential. The term itself was coined in the PKI layer cake when Dan Kaminsky, Lance Esselman, and Meredith Patterson broke the X509 search system. So they got about 20 different ways in which a CA would see a different common name in the cert than the browser that got the signed cert. So the CA was signing something, something, putting something, which happened to contain the substring PayPal, and the browser would see paypal.com. Why is that? X509 is very context sensitive and very ambiguous. It uses ASN1. ASN1 has multiple ways of encoding a string, for God's sake. Right? How many of them were there? 5 or 8, I don't remember. So making sure that parsers agree in this situation is impossible. And so indeed they did not agree. If the CA and the browser were using different libraries to parse, the parsers disagreed. That was in 2010. Which brings us to the Android master key. Sorik described that in excellent blog posts. I urge you to read all three of them. But the scheme was very simple. Here's your Android package, and you want to verify it. It's signed. You want to verify the signature. And if the signature passes, then you unzip it, then you install it, right? So simple. And of course, you don't want to write your own cryptography. That would make you a bad person. So you take an existing cryptographic library that happens to be in Java. And then your installer is in C++, because, why would you want to write Java if you can avoid it? Writing your own installer doesn't make you a bad person as opposed to writing your own crypto. So, this pipeline, except the packages are zipped and the signature sits in the compressed archive. So the verifier, the Java verifier, unzips it. And so does the C++ installer. And then it turns out that the unzippers do not agree. The Java implementation would extract a different content than the C++ implementation. Isn't that nice? I mean, unzip, if you look at that format, is very context sensitive. And, you sort of expect it. It's a compression format after all. But in the end, you installed something completely different than what you verified. And the reason for that, there are multiple reasons for that. The best and favorite reason was that C++ has unsigned integers and Java doesn't. So if you had large integers in there, Java's idea of what they were differed from C++ unzippers' ideas of what they were. And again, read all three of those brilliant blog posts. They are great. But this was a parser differential, a simple parser bug. So it wasn't fixed right the first time. Initially, patches were offered, and Java was tweaked, and then the C++ was tweaked. And this is wrong. You actually can't do this. There is a good mathematical reason for not being able to test whether two parsers are equivalent if the language that they parse is more complex than a deterministic context-free. So just to remind you of that standard diagram, regular languages accepted by finite automata, deterministic context-free languages accepted by a stack automata, non-deterministic context-free, and then it goes into weakly context-sensitive, and undecidable. Well, undecidable is bad. You can't, this is your halting problem. You can't, by static analysis, have a general algorithm to determine whether a program completes or not. And in reality, this just means that you have to run it. And by the time that you run it, it's too late. So parser equivalence is only decidable in the shaded region, regular or context-free. And zip is nowhere near regular or context-free. It's strongly context-sensitive. So you have, if you depend on the same message being parsed the same way, use the same parser. It's just that simple. And in the end, it was fixed that way. But if this is something that your security depends on, this is how you should do it. And again, this is a very simple rule, like careful with the pitchfork. Pitchforks kill. Right? Those prongs hurt. Okay. So HTTP chunked encoding, beautiful, beautiful bug. So just to recap what chunked encoding is, normally in your HTTP response, you send a content length header. Here is your web page, and here's how long the stream is, and here's the stream. But sometimes when you want to start sending a response, but you don't yet know how long it will be. Say you're going through the database, and you don't know, you don't want to interfere with the user experience being snappy. So for that, you can start sending using the so-called chunked encoding, and you indicate in the header that this is the chunked encoding by transfer encoding chunked. And then you give a hexadecimal for the length of the chunk, and then the chunk itself. And then again, a hexadecimal for the length of the next chunk, and then the chunk itself. And when you're done with the chunks, again, you don't know how many chunks will be there, but you know you're done when you send a 0. So simple enough, right? And then the question arises, what if that hexadecimal is not a small hexadecimal, but a rather large hexadecimal, right? So dead beef instead of 19, right? And here is an exploit that, here is a part of the Metasploit module for the CVE, which was discovered in 2002. Now, that's ancient history, right? So here, get HTTP, then transfer encoding chunked, then the headers end, and the first chunk starts, and it starts with dead beef. And so can you guess what happens next, right? Well, the shell code present in the chunk should sort of alert you to that. But yeah, so this is the fix. The integer was naturally declared as int, buff size. And so the fix is to correct that at the moment of the comparison and to avoid the buffer overflow and the memory corruption. So you're casting that buff size to unsized int to generate the right comparison instruction. Interesting, right? But predictable. So, you know, a simple rule, watch where you're going. Integers are tricky. Just don't step on them, that sort of thing. And then over 11 years pass till an exact same issue is found in Nginx, which is a high-profile target. Quite a lot of people have been looking at it. You know, the fix is here. Again, if your length is less than 0, then probably you're doing something wrong. And you should stop doing that now. And this is in Nginx HTTP parse, the parser for HTTP headers. So the fix was simple, you know, but why did this vulnerability sit there for over 10 years? And the answer is that's the way this Nginx is written. So Nginx is a state machine. It actually is a state machine that consumes one character at a time. And this is great. I mean, you can sort of see the structure there. You know, you see it bites off a character and interprets as an integer. And, you know, if it's a digit, then it subtracts a 0. If it's a letter, it subtracts an A and adds 10. And, you know, isn't this great? No, this isn't. Because when this goes on for thousands of lines of code, good luck determining which one of those clauses means what in your input. And, you know, so after you're done consuming this character by character, you have no idea from this code, again, what is expected, why it is expected, and how to audit this code. So just to look at some metrics, right? It's 2,300 code lines. It has 57 switch statements. And it has 272 single character case clauses. It's a miracle that the programmer could actually keep all of this in his powerful brain, and this works, and this is fast. And there is a reason why it's fast. That sort of a state machine can be made very fast. Rob Graham, in his mass scan, has perfected the art of those fast parsers. But oh my God, how do you audit something like that? The code is absolutely unintelligible, right? And you're fatigued very fast. Again, there is no idea from the structure of this code, no idea can be derived what this is doing and what this is checking for. And of course, you know, when you get to line 2043, it's easy to forget to check whether your length is a signed or an unsigned integer that just overflowed. So if you wrote this in a parser combinator style, combining simple parsers instead of writing everything out in C, it would have been found immediately, not sat there for 10 years. So again, a very simple rule. Watch where you're going. Look under your feet if you're carrying a load. And you know, just don't step where you're going to fall. Anyway, so then I had the slide deck, and then guess what happens? Shell shock, right? So it turns out that the system 3, which everyone has been using, which calls your shell, which is usually bash, actually means parse and execute environment strings. Like, you thought that you were controlling what the system would call, what the shell would get, entirely because you get to supply that string right there. And the attacker has absolutely nothing to do with it. And it turns out that there is another invisible argument. And by the way, it is being passed to the shell that it is going to parse it. And so you're thinking that, oh, I'm going to use system. I'm not going to monkey around with execve or some such because, you know, 3 arguments are worse than, clearly more complicated than 1, and we'll keep it simple. It just turns out that there is another input channel. So you think that you're invoking this all-powerful genie, the bash shell, right, that can do anything on the machine and can take any program. It's a fully Turing-complete programming language. So you think that you're, you know, invoking this genie and you're whispering into its ear in a soundproof room, and what can go wrong? Except the genie has the other ear, and it's like pointing outside. And a helpful CGI program is exposing that ear to the outside world. So to quote Dan Kaminsky, Bash is really a local app that woke up one morning on the ship CGI bin with a pounding headache. You know, referring to the old practice of hiring, actually kidnapping sailors by getting them drunk, and then the next thing they know, they're not on that friendly port bar anymore, talking to this friendly guy. They're on the ship, and they can get out, and they have to work, you know, for the next so many months while you're crossing the sea. So I posit that there's an important principle that has been violated here. And the principle is that computation power exposed to external inputs is actually computation given away to the attacker. We call this the least computation power principle. Computational power is privilege, and exposing it at a communication boundary is a very bad idea. So why do you even have your bash somewhere near your inputs? I mean, dynamite, people running around with torches, and not a good combination. Well, gunpowder, anything you like. So you don't expose your most powerful computational engine just for the sake of running one program. And everyone has been doing that because no one has been looking at this hidden flow of data through environment strings. If you were made to specify the precise expectations of your input to the system, you will have thought twice rather than saying, oh, and it will accept any string whatsoever. But, so it goes, and we have shell shock, and that was really embarrassing. So again, watch out for the long pole, right? A very simple workplace safety rule. If you have a long pole and somebody has to swing it, like stay the hell clear. It's a very important rule to observe. Keep your input away from your computation engines. So, of course, I wouldn't be standing here talking to you if we did not propose a solution. There is a secure parser construction kit called Hammer that Meredith Patterson is working on. And it is on GitHub, and you can download it. It is in C. It allows you to write parsers that read like the grammar they are parsing. So parsers that are intelligible and auditable. You can write them in C, and there are bindings for Java, .NET, Python, and other languages. So use Hammer to construct your parser, or emulate this style, at least check the style and see how you can write a parser that looks like the data, the grammar for the data it's parsing. And so I leave you with those parser commandments. Specify your valid and expected input with the grammar. Your input is a language, treated as such. Keep it as simple as possible. Avoid context sensitivity. Avoid nested field lengths. Avoid nesting objects unless you actually need it. And if you do, then keep it context-free. Don't make it so that the objects need to agree across each other. If you handwrite the parser, make sure that the parser code is intelligible and it's clear from the code what kind of inputs it's expecting. Then you will know if you have checked every assumption that you will later rely on. So use the parser combinator style. Create simple parsers first, then combine them programmatically. Do not put everything into one large wall of code where you can't see just exactly what you checked and where you are and whether you've checked everything. Don't mix semantic actions with syntax recognition. If some fields must agree, check it now. This is a matter of syntax, not semantics. Do full recognition before processing. And remember that memcopy gives power to the attacker if you fail to check any one of its arguments. Same with allocation. Those can shape your heap. So be very careful with those powerful primitives before the input is fully validated. I mean, the input is already sitting in the buffer. Delay your semantic actions till it's fully checked. And then perhaps you will avoid gaining a pony in the years to come. So we have a workshop dedicated to this. It happened last year. The papers are online, and there are, I would say, quite a few interesting papers. langsec.org has the sub-page for the workshop. You will find all of them there. And next year in May, we're going to run it again. So mark your calendars. This is the message that I would like to leave you with. Parsers are complex. There is only one way to do it right. That is to say, to actually specify the language and to write the parser code so that it is reflecting the language. And best, of course, generate the parser code with a trusted generator. But if you have to handwrite it, then make it auditable and intelligible. Thank you. And join the LangSec conspiracy. Let's make code at communication boundaries, at input boundaries, not suck. There we go. Questions? Mm-hmm. So JavaScript, right? The question is, it's presumably possible to do proper design and simplify message formats. But what about web browsers? They include JavaScript programs. And the rendering of HTML is now pretty much also execution. Now, what can we do about that? And JavaScript. I mean, this really grinds my gears. Like, imagine, this is a language where, so I was taught that in programming languages, people never handwrite parsers. In programming languages, people determine people write out the grammar, right, the syntax, and they have the Becker-Snor form, and then they use something like Bison, Lex, and Yak to generate the parsing code. And, you never would see a handwritten parser, and you never would see a parser bug when the program crashes the interpreter while it's being parsed, right? While it's being loaded. No, we're not talking about a program running out of memory. No, just program crashing the interpreter code. Guess what happens with JavaScript? Now, this thing is a steaming pile of manure, right? How can you hope to build anything secure in a language which you can actually crash with a program in that language, right? So I'm not talking about the handling of the data values being inconsistent and non-intuitive. I'm not talking about that. If you look for this video called WAT, W-A-T, it gives you examples of JavaScript syntax, and then asks you, well, what does this produce? And you can never guess. It's just that the language was designed in a very ad hoc manner to accommodate a very fast development cycle. But, good luck trusting that. You can't. All you can do is isolate this with layers and layers of isolation. And even so, it will shape your heap. So, realistically, just do not trust an environment that has don't build trusted environments on that kind of technology. It's engineering, real-world engineering, is based on a clear understanding of impossibility, right? There are energy conservation laws. In the early days of locomotives, people were thinking of how to make the guard on the front of the locomotive in such a way that would not hurt the person who happened to be across the tracks. And there were all sorts of cushioning schemes and sweeps and, In the early days of railways, cows would get hurt all the time because they just roamed free next to the rail line. And then people realized that no matter how many cushions you put in front of a train, the energy that ends up in the cow will smash the cow. And you can't help this. And so engineering, the reason why houses stand and planes fly is because people understand that certain things are impossible in our world and they work around them. Those people are called engineers. They build engines. Now, if you ask a software developer what is impossible in our software development land, you will not get a clear answer most of the time, right? There are certain tests that should not be attempted with improper tools. Normally you want your code to be provably correct, and your debugging is the approximation of this process. Now, there are problems where you can't provide the proof, where you can't possibly provide a procedure that would work. They are called undecidability. Turing completeness brings the heaviest one of them all, undecidability. You can't, by static analysis, determine any non-trivial property of a program, such as halting, but any non-trivial property at all. So this can't be done. It shouldn't be attempted. Trying to build secure systems on Turing-complete languages that need to take hostile Turing-complete inputs is the same as trying to build a perpetual motion machine. And we're now in the stage of early perpetual motion machine inventors, right? I have another slide about that, actually. It's just, let me, how badly am I doing on time? Okay, so I will show you that slide, just so. Yeah. Don't review. Okay. So, hey. Right? In 1494, Leonardo da Vinci, who was quite an arms dealer himself, you should read his CV where he is writing about his accomplishments and lists all kinds of impressive military tech that he will design if he gets the money from the Duke of Milan. He wrote this in 1494. O ye seekers after perpetual motion, go and take your place with the alchemists. But we're still in the stage of trying to build impossible systems. And this has to stop. There is this expectation of magic from computing systems. But just as engineering is based on knowledge of impossibilities, so should be software engineering. That was a very long-winded answer. Other questions? So if not, I will conclude with this quote. So Norbert Wiener, who coined the word cybernetics, who started the discipline, said one of the chief duties of a mathematician in acting as an advisor to scientists is to discourage them from expecting too much of mathematics. The reason he said that in 1964 was that mathematical modeling was seen as magic back then. You sprinkle it on any area of human activity and you get instant improvement. And he resented that. Now, we see the very same belief in the magic of computers, that you can sprinkle them on any area of human activity and get instant improvement. We see it in politics. We see it, we see people claiming that, oh, if we only had more computers, more electronic things in healthcare or power grid or other things, then it would magically improve. And this is just not true. This is the most insightful quote that I've ever seen. Unfortunately, it's kind of hard to get. That was a technical report from the Yale University, which is not known as much as it should be. It said that physics that describes the boundaries of what can be done does not break down at the symbolic level of human activity. Even though it seems that symbolic manipulation that computers do is just so simple and almost free of energy expenditure, it doesn't mean that there are hardness, impossibility results in there. So physics does not suddenly break down at the symbolic level. You can't build symbolic structures for free, no more that you can build material structures for free. And so I would steal this winner's quote and turn it around and say, one of the chief duties of a computer scientist or a hacker is, in acting as an advisor to everyone at all, is to discourage them from expecting too much from computers, until and unless we understand that some things are impossible to do. And we base our computer engineering on a clear understanding of what the impossibilities, what the laws of nature are in our field. And I leave you with that. Thank you.